Welcome back. In the previous lesson, we covered the fundamentals of fiber optics: Snell's law, total internal reflection, fiber structure, and light sources. Today, we go deeper into fiber types and then explore an exciting wireless technology called free space optics. We will finish with a complete comparison of all transmission media. Let us start with a closer look at single-mode versus multimode fiber. Single-mode fiber has a tiny core of just 9 microns. Light travels in a single straight path, which means zero modal dispersion. This gives single-mode fiber extremely high bandwidth. Repeater spacing is 50 to 100 kilometers, and some systems achieve repeaterless links over 20,000 kilometers. The wavelength of 1310 nanometers gives minimum dispersion, while 1550 nanometers gives minimum attenuation. Single mode is the backbone of modern telecommunications and submarine cables. Multimode fiber has a much larger core, 50 over 125 or 62.5 over 125 microns. Light bounces through the core in multiple paths, called modes. This causes modal dispersion, where different modes arrive at different times. Multimode supports up to 200 megabits per second over distances under 100 meters, making it ideal for local area networks within buildings. Multimode fiber comes in two important varieties: step index and graded index. In step index fiber, there is an abrupt change in refractive index between the core and the cladding. Each mode, or ray of light, takes a different path through the core. Rays bouncing at steep angles travel longer distances than rays near the center. The result? Different modes arrive at the receiver at different times. This pulse spreading is called modal dispersion, and it limits both bandwidth and distance. Graded index fiber solves this elegantly. Instead of an abrupt change, many layers of glass are applied, each with a slightly lower refractive index as you move outward from the center. Light rays in the outer layers travel through lower index glass, so they move faster. Light rays near the center travel slower, but take a shorter path. The result is that all modes arrive at the receiver at approximately the same time. Graded index dramatically reduces modal dispersion. Now, fiber cables also come in different physical constructions. Tight buffer cables wrap a 900 micron coating directly around each fiber, making them flexible and easy to handle for indoor installations. Loose tube cables place the fiber inside a larger tube filled with gel, which protects against moisture and temperature changes. Loose tube is preferred for outdoor and underground installations. Now let us explore free space optics, or FSO. FSO is wireless optical transmission through the atmosphere, using infrared light instead of radio waves. In the United States, only 5% of buildings are connected to fiber, but 75% are within 1 mile of the fiber backbone. FSO bridges this last mile gap. Each FSO unit uses a high-power laser and a lens to transmit light through the air to a receiving lens on another building. It operates at wavelengths around 800 and 1550 nanometers. FSO offers impressive capabilities: 100 megabits per second up to 2.5 gigabits per second, full duplex communication over distances of 1.5 to 2 kilometers. Line of sight is required, just like microwave. However, FSO faces several atmospheric challenges. Fog is the biggest enemy. Fog droplets are only a few hundred microns in diameter, close to the wavelength of the light, causing severe scattering and absorption. Scintillation occurs when heated air creates temperature variations, causing the signal to dance and fluctuate at the receiver. Absorption happens when water molecules in the atmosphere convert light energy into heat. Building sway from wind or seismic activity can misalign the transmitter and receiver. Solutions include multi-beam systems, divergent beams, and shorter link distances. Let us now compare all 5 major transmission media side by side. Twisted pair operates from 1 MHz to 1 GHz, with bit rates from 2 megabits per second up to 1 gigabit per second. Its bit error rate is 10 to the minus 5. Repeater distance is just 2 kilometers to 100 meters. Security is poor and cost is low. Coaxial cable operates at 1 GHz, reaching 565 megabits per second with a BER of 10 to the minus 7 to minus 9. Repeaters every 2 to 3 kilometers. Good security. Moderate cost. Microwave covers 300 MHz to 40 GHz, up to 622 megabits per second with a BER of 10 to the minus 9. Repeaters at 30 to 70 kilometer intervals. Poor security, moderate cost. Satellite uses 390 MHz to 30 GHz, reaching 155 megabits per second with a BER of 10 to the minus 9. Coverage from 800 to 36,000 kilometers, but poor security and high cost. Fiber optic is the champion. Operating from 750 terahertz to 194 terahertz, with bit rates from 2.5 to 10 gigabits per second and potential for 150 terabits per second. BER of 10 to the minus 11 to minus 13. Repeaters at 50 to 100 kilometers, extendable to 6,000 kilometers. Good security and moderate to high cost. For our practical examples, a link between Turkey and Germany, satellite or undersea fiber, Ankara to Istanbul backbone, fiber, office LAN, twisted pair, Erzurum to Trabzon across mountains, microwave, cable TV distribution, coaxial. Let us summarize today's lesson. Single mode fiber. 9/125 micron core, laser source, 50 to 100 kilometer range, ideal for telecom backbone. Multimode fiber, 50 or 62.5/125 micron core, LED source, under 100 meters, used for LANs. Step index causes more dispersion due to abrupt refractive index change. Graded index reduces dispersion by gradually varying the refractive index. Tight buffer cables for indoor, loose tube cables for outdoor installations. Free space optics bridges the last mile with laser links through the atmosphere, but faces challenges from fog, scintillation, and absorption. Among all transmission media, fiber optic leads in bandwidth, bit error rate, and distance, while twisted pair remains the most economical for short distances. The right choice depends on the application, distance, bandwidth, environment, and budget. In the next lesson, we will explore circuit switching, packet switching, and the structure of the public telephone network.